the sort of smooth paradigm in field theory. So the standard approach to field theory starts with a choice of a metric manifold, which we call a spacetime. Then, and this is assumed smooth. Then there is a smooth manifold, which is the total space of the configuration bundle. On it, we have some smooth tensors, like the metric for the Klein-Gordon Lagrangian density.
Excuse me, what bundle is this bundle?
It's the bundle whose global sections are the fields of the theory.
Yeah, but this is not a geometrical, this is a fiber bundle?
It's a fiber bundle. It's a fiber. Yes, and then you consider its globally smooth sections as fields of the theory. So these will be the smooth fields, and then there is a distinguished functional on the space of such fields whose critical points are the classical field configurations. And that's the standard approach, general as it stands at the moment. Instead, today I'd like to advocate a more general approach in which everything I've said will be true locally, but then there will be domains in our space-time over which everything will be as before, but they will be separated by codimension one domain walls, which will make local objects defined on domains talk to one another. So to each domain, there will be assigned a smooth configuration bundle, but there may be different configuration bundles associated to different domains. And then the whole point will be in assigning to the domain walls and their intersections further data, which will make the phases of the theory as associated with domains talk to one another in a coherent manner. Think of it as some kind of sheaf of field theories, and there will be a notion of gluing between the various local sections of that sheaf.
So what do we glue? We do not glue the space-time?
Oh yes, we will glue space-time. We'll have the space-time is just decomposed into, split into domains. And there are domain walls, and these intersect as higher codimension.
Space-time is the manifold?
The space-time retains its manifold structure. Yes. All right.
Only this bundle is not.
Yeah, and the data that live on it, like the tensorial data, and you will see more general situations. First, let me walk you through a case in which this kind of sheaf theoretic description is a choice and not a must. So I want to show you how this is Monsieur Jourdan, who has spoken prose 40 years without knowing it, and likewise we will be confronted with a field theory in the standard smooth paradigm in which this sheafification, let's say, will be seen to occur as an option, not as a must, but then we'll learn how to generalize this to situations, which I will define later on, in which this is actually a must. So let me first start by telling you what I mean by a field theory.
What is LFT?
So Lagrangian field theory. A Lagrangian field theory. So I start with a space-time, then I choose a fiber bundle over this metric space-time, with a typical fiber modeling the space of internal degrees of freedom of my field theory, and then global sections of this bundle I call fields, and then there is a distinguished functional on the space of all such sections whose critical points are what I call classical field configurations.
Sections will be with compact domain.
No, I don't. I'm not assuming anything else.
How can you define this action function?
Well, you may impose conditions on the fields, right? But anyway, this will not be the main sort of problem. But yes, you can impose conditions on the section. Like some kind of compact support, right? So now I want, since symmetries will be an important issue in my talk, I want to say what symmetries are in this context. So these will be sort of vertical automorphisms of the bundle that cover identity diffeomorphism in the base, and then the group of sort of the symmetry object could be a group object in the set category. It could be a topological group. It could be a Lie group, whatever you use. And then I call these symmetries global. symmetries if they stabilize pointwise in the group this distinguished functional. Typically, what we encounter here is a trivial bundle where you're just dealing with smooth fields from space-time to the space of internal degrees of freedom. And now there are two contexts in which, as I said, there is no must, but there is an option to see this local structure of locally smooth objects which you glue along codimension 1 domain walls in space-time. Yes?
Could you go back
Sure.
one slide? This, what you encircled in red. What is this? This is a particular definition of invariant section? Or
Yes,
what
I'm considering invariances of the action function.
So
there is
fields which are invariant.
Okay,
Not fields.
so
the
sigma
whole
S on lambda H phi must be as phi for any H in the group.
So
S is the action
not
function.
section but function. Oh,
Yes. And I have been used map on sections and this is all right. So the first context in which this kind of sheafification occurs is that of nonlinear realizations of symmetry. So we start with the field theory as before, select its critical section, physicists call it a vacuum, and then this has a stabilizer in the group. So we have some kind of group of global symmetries of the action functional, and within this group there is a closed subgroup which stabilizes this particular field configuration. And then under certain algebraic conditions on the decomposition of the Lie algebra of the full symmetric group into the Lie subalgebra of the stabilizer and its direct sum component, namely reductivity, which stands here, you may try to model field theory of excitations around the vacuum. This was the question that was posed by Schwinger, Weinberg, later Isham, Stratby, Coleman, and many others. And then what they set out to do was thinking up a model of a field theory with the space of internal degrees of freedom defined by G mod H, by this homogeneous space. And then the way to proceed is the following. You could just go straight to G mod H because this is a smooth manifold, but instead, and this is the option, not a must, but it's well motivated, is you go to G, which fibers principally over G mod H, and since you want to have a manifestly G invariant field theory on G mod with G mod H as the space of internal degrees of freedom, you look for invariance of the G action in the Cartan calculus on G, namely you look for H basic forms that descend to G mod H. You realize G mod H through local sections of this principal fibration, and then using these local sections, you pull back H basic forms from G down to sigma.
Is this G acting transitively on fibers or not?
G is acting, G is acting transitively on fibers, yes. You have the standard induced action of G on from the left.
So the fibers, I mean, those internal degrees of freedoms are initially G, yes?
I would say the following: you model G mod H as a collection of sections. This is the collection of sections within G. These are the sections of the
G principal bundle? Or?
It's an H principal bundle. So you have G fibering principally with the.
But is this reduction of this G principal?
No, but previously.
No. So this is my space of internal degrees of freedom. J fibers principally with a typical fiber H, and I map G mod H locally, of course, into G, and from G I pull back the H basic forms.
I'm afraid you didn't tell us that G acts transitively on fibers.
No, but
Look,
can you
yes,
come back with one slide? No, because you started from some field theory with this F as a fiber bundle.
That was
And
to
then
say
you
only
can-
how this thinking arose historically.
Ah.
People had a vacuum of a field theory and they wanted to model the vicinity of the vacuum. And they looked at a reducible symmetry, reducible component of the vicinity, which naturally, equivariantly is modeled by G mod H. And then I want to write down a field theory with the space of internal degrees of freedom, G mod H, with left G invariance. That's it, no more to it, okay? And then I model this G mod H by local sections into G. And then why is that so? Because I have a natural choice of H invariant, H basic forms on G provided by this Cartan calculus if reductivity is enforced here. All right, so what picture are we getting here? Well, we have contributions from sigma alpha in this particular case, which glue smoothly. We don't have to put anything on the, maybe I should go one slide back. We don't have to put anything on domain walls between sigma alpha, because these objects glue smoothly, since we're defining our field theory in terms of H basic tensors. So they simply, these are the ones that descend to G mod H. So yes.
So what are ingredients here? Is a principal bundle, say?
I have said what the ingredients are. I want to have a field theory with internal degrees.
You have also a principal bundle.
No, this cannot be principal because then you have fixed elements of the action.
Yes. Yeah. Look, if I may, this is motivational piece. We're not there yet, so. Okay, let me storm forward, nevertheless. And
So
mind
this
you,
is
yes.
a fiber bundle on which G acts transitively on fibers, yeah?
Yes, it's a trivial bundle, sigma times G mod H, and with an action on G mod H from the left, induced from the left
Yeah, but
translation.
Forget H, yeah, but this is before, so your original playground is the fiber bundle on which G acts transitively on fibers, yeah?
Yes. Well, no, I'm not assuming any transitive action. There it was completely general. I have an action of the group. I'm not assuming anything about it.
No, but if this is not
Wait.
transitive, then of course G mod H is not the mod.
Wait, we're jumping between the general framework and this one. In this case, I have a G mod H as the space of internal degrees of freedom. I have sigma times G mod H as my configuration bundle. On G mod H, so the fiber, the typical fiber of that bundle, G acts from the left in a manner induced from the left translations on G. That's it. There is nothing deeper in this. All right, and we have we get a well-defined Lagrangian field theory in terms of those invariants for smooth mappings from sigma to G mod H, modeled within G. So with this stratified configuration space given here. All right, so that's the first example. The second example is much less trivial. That's gauging via defects. That's what I would call it. So the idea here is the following. So so imagine you have identified global symmetry group in your field theory. So this is the configuration bundle of my field theory. There is a group acting vertically, and I'd like to gauge, if I can, I'd like to gauge, so render local, this global symmetry group. That means I would like to perform a reduction, pass from the space of internal degrees of freedom F, which is the typical fiber of this bundle, to F mod G, except that F mod G may not be smooth. And then
but the transitively is crucial for that. Yeah?
yes, true. Yeah, but I didn't gauge there. I didn't gauge G there in the previous example. I gauged H, and of course it was transitive.
Yeah, that's clear.
Okay, so the idea here, that ultimately goes back to Cartan and Borel, is to replace the original configuration bundle with another bundle over the same space-time. That bundle will have the same space of internal degrees of freedom, so the same typical fiber. But the crucial point is that we will act upon it with a fiber of groups, each of them being non-canonically isomorphic with the group of global symmetries that we're gauging. And this will be a fiber-wise action of this bundle of groups, each of them being G, that's the typical fiber, on this bundle of fibers, each isomorphic with F. And the idea to proceed here goes back to Cartan and Borel. Since we're ultimately interested in descending the dynamics from F to the orbispace F mod G, then the right thing to look at is the so-called mixing diagram by Cartan and Borel, which is the sort of universal picture behind the standard physical construction. So the universal picture starts with the mother of all principal G bundles. That is the universal principal G bundle over the classifying space of the group. This we may use to construct the products of its total space with the space of internal degrees of freedom of the original field theory. And since the action of the group on the total space of the universal principal bundle is free and proper, we have the quotient manifold theorem, which gives us the universal associated bundle. And the point here is that the universal associated bundle, on the one hand, it fibers over the same base with the fiber given by F. So that's our thing. And on the other hand, if the orbispace is smooth, then it also fibers over that orbispace with a contractible fiber EG. So this is a homotopy model of the orbispace. And now, if you recall that any principal bundle in the topological category over a given manifold can be obtained by pullback of that universal structure from the classifying space of the group, then what the physical construction does, and here we see its rationale, it's modeling the reduction, even if F mod G is not smooth, is you sort of pull back this mixing diagram to the space-time of your field theory, and in this way you obtain the so-called associated bundle, which has the typical fiber given by F, and it's acted upon by the adjoint bundle, which is also an associated bundle, just the association is through the adjoint action of the group on itself. All right? And now,
So what is PG?
So it's a principal G bundle over your space-time for the group G. And it's obtained.
Particular one or just a bit?
Well, you will see that we have to take all isoclasses. That will be the point. You have to sort of resum over isoclasses. So resum over the homotopy classes of these maps. Okay, so now the
No, but in this picture, this is
a bundle, a principal bundle. Yes, indeed. So now the interpretation of the objects in the game is the following. I have global sections of this principal bundle, which has the typical fiber F. So these I call fields of my theory with the symmetry gauge. And we have global sections of the adjoint bundle as so-called gauge transformations. But this is very unwieldy because, you know, we have this quotient construction, so
this is adjoint with respect to what?
The associating action is the adjoint action of the group on itself. It's all right. So this is unwieldy. So let me do it wieldy. The convenient rephrasing is the following. You see this structure, a group acting on a space, is bijectively mapped to the following one. You have the space of G equivariant maps from the total space of that principal G bundle which entered previously, PG, into the typical fiber of the associated bundle. And this is acted upon by bijectively mapped to the gauge group, the space of G equivariant mappings from PG, again, into G. And so now, equivalently, these are my fields, and these are my gauge transformations. Why is this useful? Well, typically you start with a given Lagrangian density and you want to gauge a symmetry. So you want to play with objects of the same time, mappings from space-time to respectively F and G, and just correct the Lagrangian density so that now the new Lagrangian density is invariant under the action of the bundle of groups and not just the group. So you see, you have PG here, and PG is locally trivial. So you may pull back the fields by local sections of the principal bundle, thereby obtaining the ingredients of your field theory. Locally smooth maps from domains of trivializations of PG into F and into G. And that you can already plug back into the original Lagrangian density, except that now, of course, it's still globally G-symmetric, but it's not locally G-symmetric, so you have to correct. But the point I'd like to emphasize here is that the picture you're getting is that of locally smooth objects over domains in your space-time, sigma alpha. And now they're glued by the transition mappings of PG. So they're strictly non-continuous if PG is not trivial. If it's trivial, then of course G alpha beta can be chosen unital, and there is trivial gluing. But otherwise, these will be discontinuous field configurations. Okay. So now, of course, for dynamical fields in the original Lagrangian density, so whenever there are derivatives, this is not the end of the story, but you have to replace tangent. Yes?
To understand well, so P is
a principal boundary.
Principal boundary with which fields, and F is a matter field.
F it was a matter.
Yes,
matter. Yes.
So matter fields in the external gauge theory.
Oh, that gauge symmetry gauge theory will come right now, because we have to horizontalize derivatives, which. That's the point. I start with something known and give it a slightly different perspective so that it can be generalized. Okay. So what you have to do in a field theory in which there are dynamical fields, so derivatives are in the Lagrangian density. Small f is a section. It's a field taking values in f. And now I replace it with those phi alpha, and I cannot simply differentiate it because this behaves ill under x-dependent or sigma-dependent gauge transformation.
What means this nabla?
Well, I have written it here. This means the nabla. It's the standard differentiation corrected by the so-called Crittenden, derivative, which is the way to induce differentiation, proper differentiation, geometric differentiation of sections of an associated bundle if you have an principal Ehresmann connection on the principal bundle. There is a way to do it.
So it is just the covariant derivative of
that's what
associated bundle.
that's the covariant derivative.
This is those names that you mentioned.
Except that typically the fiber of this associated bundle is a vector one, and so you don't really know the full story. I mean, the one that you teach to students is typically it's a vector bundle, so the form of the covariant derivative is very particular. But there is a more general object. Yes.
But have you fixed a principal connection on something?
Well, I'm saying that you have to choose it. You have to choose it. Well, it always exists, as we know. Principal connections on principal bundles always exist.
So this number has no meaning before you choose the.
Absolutely none.
Okay.
Absolutely none.
But you didn't choose it before.
No, that was in the topological category. And that was a motivation that I want to model the reduction to F mod G. That's what I'm doing.
But usually in gauge field theory, the connection is kind of a field. So it's
of course.
chosen.
Of course, I mean,
it is...
you look, a connection is a connection one form, and if you pull back the connection one form by those local sections of the principal bundle, you get one forms, locally smooth one forms on your space-time, on sigma alphas, with values in the Lie algebra.
So
these are the fields.
Yeah, so this is the dynamical part, and the matter part is in F, yeah?
So the sort of topological part was there, and now if we have derivatives, we have to plug in the external gauge field.
Connections of P are potentials. Not yet fields.
No, okay.
Yeah. It's not. They're not like well. Plus, they're not dynamical. We don't. It's background. It's a background. But it's better to really think of this as a geometric operation which horizontalizes derivatives, and that's it. Okay. Anyway, so what we have as the upshot is this Lagrangian field theory defined in terms of locally smooth mappings into F, which are glued at domain walls. So the domains are the domains of trivializations of PG, and the gluing is by transition mappings of the principal bundle. And now, if we could do with just trivial principal bundles, then we'd be safe because we could always choose as gluing, as transition mappings, the unital transition mappings, and we would have smooth fields. But remember this motivating story of the universal object.
So you use instead of open covering of the base manifold, so space-time, as you say.
Yeah. No, I use a trivializing open cover.
Stratification.
Well, you could call it stratification. That will kick in one. Yes.
So they don't intersect in an again open subset, but along.
Well, I could always use a good cover.
So
I assume the word C2 category, so I have while around, which means that I have good covers, and every cover can be refined by a good cover.
So if I can make, Rafał, a conceptual remark. So in this gauging situations, right? So you always have a homotopy model, but in general, the fiber of that is infinite dimensional. So essentially what he's trying to do conceptually is to find a smooth model of that with a finite dimensional fiber. So you cannot find a smooth model, but you can find a piecewise smooth model where these, if you allow for these discontinuous gauge transformations. That's
one thing, and of course the other thing is that since I have lost this universal picture, I have to take all principal bundles, or at least all isoclasses of principal bundles. So if my space-time is non-simply connected, I will have non-trivial principal bundles. And that means I will really have this twisted sector in which I won't be able to glue fields on the nose. All right. So yeah. So let's try to pinch this.
So what is new in this picture?
Well, what is new in this picture that we no longer play with globally smooth objects, like globally smooth fields, which were previously into some space of internal degrees of freedom, global tensors on the configuration bundle. Look, you have A alphas, which are defined only locally. You have phi alphas, which are discontinuous across the walls that separate domains of trivializability of the principal.
I think you pass at some point to global objects.
Well, that's the point of descent. I mean, you have ultimately, you know, and that's the point. Ultimately, you know that you are just representing a global section of the associated bundle. So there is a globally smooth object. I'm just representing it in a way which looks discontinuous. But it's good to have it because it explains a lot of things, like what is this gauge field theory? You're really modeling a theory into F, but with the twisted sector. So you're allowing field configurations which jump, but only by what? By something that disappears as you pass through the quotient. So if you act by the group action which you're gauging out in the reduction, then of course you may allow such discontinuous field configurations. And now what are we getting? So as you said, we really get a stratification of our space-time. We have a bunch of domains of trivialization of the principal bundle. Then there is a bunch of intersections of those domains, and then there are triple intersections and so on. And as it happens, you can form a simplicial object, and that's the first instance of a simplicial object kicking in, and that's the check nerve of the open cover. And over this, what is the importance of this check nerve? Over it, there is a simplicial one form, which defines for us the field theory. So there are one forms on sigma alphas and U1 value, well, G valued mappings over their double intersections, which satisfy certain simplicial identities defined in terms of the Dupont top boundary operators associated with this simplicial manifold, as with any simplicial manifold, there are associated in terms of its face maps certain cohomological operators defined by Dupont in the 70s. All right. So now you might say, okay, but after all, I've just refurbished something that was known, and you can do without the discontinuous object. So I'd like to now give you a context in which this discussing a field theory in terms of rather sheaves of field theory rather than single field theory with everything inside smooth becomes a must and not an option. So what I'd like to discuss is our rigorous models of geodesic dynamics of extended distributions of some charge, in which we have sort of geodesic embeddings of, for now, closed d+1 dimensional manifolds into metric manifolds.
So what is this square bracket sigma n?
The smooth mappings.
Oh,
Smooth mappings.
Oh.
Well, there's a reason why originally I wanted to pass to the Z2 graded category as well, and then I would. But anyway.
May I ask for explaining notation?
No, you may not. It's jet lag. I wanted to discuss something sort of more general. Yeah.
No,
yeah.
okay, but if you want people to understand, and
Well, I just explained it. It's smooth mappings.
at the
Smooth
moment you
mappings.
did.
My fancy for calling smooth mappings. Okay, this way. So we have smooth mappings embedding sigma into M. M is metric in a geodesic manner, and this geodesic embedding, so minimal with respect to the induced metric, is distorted by Lorentz type forces. So there is a closed d+2 form on M, and I want to consider the following embeddings of sigma into M. So the left-hand side, if it were equal to 0, would just describe a minimal embedding. So it would be a geodesic equation, or it would be the equation of a minimal surface in the induced metric on sigma, or a minimal volume or whatnot. If it was 0. But now the 0 is replaced by Lorentz type force. Yes.
But I have problems with C. One is G, and on the right side, what is Q? Or
Q is a parameter, and mu is a parameter.
Q
Mu is like a mass.
So this is not the same G, no?
Q is Q, not G.
Q.
Yes, Q. This is a Q, and I even said that it's a topological charge, for what it's worth, and then this is a gravitational charge, for what it's worth. All right, and now, as for the left-hand side, it's easy to model it in a Lagrangian manner. You can choose your volume Lagrangian, or your energy, your volume action functional, or an energy action functional. The difference between the two formulations, which is the reparametrization invariance, will not play a role in this talk, although it does play a role in general. And then the problem is in modeling the right-hand side. Ideally, you would like to write the Lagrangian density as follows. You would just pull back the primitive in the RAM cohomology of H, except that H may be non-trivial and there is no global primitive.
So what is H here? H was a
H?
subgroup at A.
No, well, sorry. H now is a d+2 form, which is closed. It's think of d equal to 0, and then it's a Maxwell field.
Okay, but
It's a Maxwell
your meaning of it.
Yeah. Well, all letters have been taken, so yeah. A friend of mine is using actually the Cyrillic, and I'm sometimes using Ivrit, but it confuses people even more. All right. So now the point is that we'd like to discuss Aharonov-Bohm type effects in this field theory. So we'd like to consider sort of coterminal histories of the elementary object, which for d equal to 0 would be just a point, a configuration. We have two histories of a configuration, and the point is to consider coterminal trajectories, coterminal histories. That's in the spirit of Dirac's 33 or 37, I forget, argument, which gives a semi-classical or semi-quantum meaning to the classical action function. as describing the amplitude of the passage from the original configuration to the initial on by sort of taking into account contributions from co-terminal trajectories.
What is he? Something is
Right.
written downstairs, but I
Yeah. So the point is that you see, we're not at liberty to choose our age, say. I will discuss a particular example, and it may happen that age does not admit a primitive. Then we cannot simply exponentiate the topological part as written of the Lagrangian density as written before, because there is no such thing. But we're putting in something here and impose conditions. And the conditions are the following. So it's something to be found. It's something to be found. Something to be found, and it's to be found by solving the constraints.
Because I never know whether it was already present.
Yeah. Thank you for asking.
Refers to the next picture.
Yeah. So I want to fix chi by imposing the following conditions. First, I should have extensivity of chi with respect to independent trajectories. So if I compute it on two non-intersecting trajectories, then it should be just the product of the two. That's the U1 counterpart of the sum of two actions for two non-interacting systems, the sum of actions for each system. And the other property is that I should like to derive the same field equations as before. And if you think for a while, this means that if I evaluate, remember I chose specifically to model closed trajectories, so to speak. They're not physical, they're pairs of coterminal histories. So sigma is closed, so it has no boundary. So now if this no boundary thing is a boundary of something, then I want this equation.
So omega is again something. Two-dimensional.
No. Look, for any d plus 2 dimensional chain in M, in which X maps my sigma, if I evaluate this chi on the boundary of this chain, then it should give me the following result.
This is chain in what sense?
In singular homology. In homology.
Okay.
Well, just a d plus 2 dimensional manifold.
Okay, you have also boundaries of
Yeah.
open subset, etc. So
All right. So I have
It's a Chiga, if I may know, he's trying to construct a Chiga-Simons character, this exponential.
So that actually fixes chi as an object.
X of sigma is a submanifold, yeah?
Yeah.
And you interpret it as a chain, or?
And I interpret it as a chain in M, yes. I think of it as a chain, or rather chi can be defined on chains, and among those chains I have images under X of sigma, okay? And so chi, satisfying these two conditions, is what is known as the Chiga-Simons differential character. So Chiga-Simons differential characters are abelian group homomorphisms from the group of co-cycles, d plus 1 co-cycles in M, cycles, d plus 1 cycles in M into U1. And there is another piece which we saw before, which is our field H, basically. And not any one, but those which satisfy precisely this equation.
One moment.
Yeah.
So you interpret M as a complex, or
Well, I think
Sibu complex? Or?
indeed. Let's put it this way. Yes.
Not
I
as
think,
just as a meaning, because cycle mean has
indeed.
no meaning actually.
Of course. No, I work with cycles in M, okay, of its singular homology. Yes. Okay. All right. So there are such objects, and of course there is a way to create them. So I shall now discuss how to define such a Chiga-Simons Chiga-Simons differential character. Sorry, given the original H. which was our initial datum. Okay, so you know how things work for d equal to 0, so how a Maxwell field geometrizes. So let me do it for d equal to 1. So we start with a 3 form on n, which is closed. If that 3 form has integer periods, then I always can, and in general that's the definition of a higher geometric object that I will be dancing with, that I can define a surjective submersion over n on whose total space there is a global primitive for the pullback of h. Okay? Then I take m fibered per groupoid of the surjective submersion, take its nerve in the standard sense, and over it I construct a higher geometric object, which looks as follows. So over the n fibered square of the total space of the surjective submersion, I have a principal CX bundle with connection whose curvature is fixed as basically the difference of the two pullbacks of B by the canonical projections. And then over the m fibered cube of that surjective submersion, I have a choice of a connection preserving principal bundle isomorphism between, I should maybe write it, projection 1, 2, pullback L. There is a certain tensor product on principal bundles with an abelian group. Let me not go there. Projection 2, pullback L. Projection 1, 3, pullback L. Okay, that's what I have here. A concrete isomorphism, which I furthermore request to be a groupoid structure on the fibers of the bundle L. All right. So among such objects, you have trivial gerbs, namely those which come with a global primitive for H in the first place. So then what you do is you take as the surjective submersion the manifold itself. There is the 2 form on it, which trivializes the exact 3 form, and then I can take the trivial principal CX bundle with a trivial connection 1 form and a sort of trivial groupoid structure. Let me not tell you exactly what it is, but there is its natural trivial structure. And so this geometric object, devised originally by Michael Murray and Danny Stevenson, his student, is what is known as the gerb. All right. So that's the neat sort of global picture, but there is also a non-neat picture that washes washes well with my idea of having decomposition of my space-time into domains separated by domain walls, which then intersect. So you see, I can first of all cover my manifold M with opens. Take a good open cover. So one such cover whose multiple intersections are either empty or contractible. Yes.
Did you really need these walls, or they can be just
in order to write down a specific formula for the hologram, for the character? I do. Yes. And furthermore, there will be stuff living with it.
Check cohomology.
Yeah, that's what I'm doing. Precisely that's what I'm doing. Except that not everyone, the students are not that familiar, well versed in Czech cohomology, so I have to describe it in a some roundabout way. Precisely, I'm doing Czech cohomology. I'm trivializing locally H, so I have local 2 forms on elements of an open on contractible opens in M. Then on their contractible intersections, I have locally smooth 1 forms, which measure the difference between 2 primitives, 2 local 2 form primitives. And then on triple intersections, I have U1 value transition mappings, which satisfy a 2 co-cycle condition in Czech cohomology. All right. So I have attained the goal of sort of describing.
This is not always possible. So only.
Well, that's why I said that I wish my H to be integral.
Okay.
That's the point.
Did you
I said that. I happen to say that. And then you can actually write the differential character as you would have written it in the first place. So you just, instead of a 2 form, which was the inverse of H, I have now a simplicial 2 form, but over a simplicial decomposition of my spacetime, and I just have the same, exact same formula, but this integral is a sum of contribution from domains, edges, so walls between domains, and trivalent junctions, because I choose a honeycomb tessellation of my spacetime sigma. But the formula is the same, I'm just dancing with different objects. I have a simplicial 2 form, I have a simplicial decomposition of my space-time. All right. Okay, so let me continue a little longer and then I make the other half shorter. I like to come to logical to conclude a logical whole. So now, the relations satisfied by this simplicial 2 form, as I called it, make it representative of a class in Beilinson-Deligne cohomology. And as it happens, and I'm just saying this to say the next statement, which is Cheeger-Simons differential characters give a model of Beilinson cohomology, of this Beilinson cohomology, which means, in plain language, in plain English, that if I fix holonomy, I have fixed the isoclass of the germ. So if 2 germs have the same holonomy for any surface, then this means that they're isomorphic. Yes, Pavel?
What is omega 1 in the Deligne?
Come again? What is what?
Omega 1. What is
Omega 1 are locally smooth 1 forms. It's the sheaf of locally smooth 1 forms on M.
on that?
On M. These are locally smooth 1 forms, these are locally smooth 2 forms, and these are locally smooth U and valued maps.
It's a different story.
Yeah.
So what?
Well, you could also resolve it by into R.
Fine.
So what is the difference in your understanding between locally smooth 1 forms and smooth?
They locally smooth ones needn't extend to globally smooth ones over N.
So they are simply local.
They're local. They're smooth there.
Okay.
They're local.
Okay, so this is not locally smooth, but local smooth.
Yeah, smooth where it exists and then doesn't necessarily
Yeah.
extend. Yes, yes.
Because of course, locally smooth might refer to global.
That's what I meant by the. Now, that's one example. Yes, precisely. Yeah. The AIs were just example. So
I
now
think
let me give you an unexpected bonus of, well, so not only are we rigorous here, but as it happens, classes of data, so isomorphism classes of gerbs, define isomorphism classes of principal CX bundles with connection over the loop space, which is the configuration space of our model. And so, and not with any connection, but the curvature of the connection of the induced principal CX bundle over the loop space, which is the configuration space of my field theory, the curvature is the presymplectic form of my field theory. So that's the first step towards frequentization, and that directs our eyes on where we should look for symmetries of this field theory. So symmetries should be automorphisms of the germ, except that we still have to understand what automorphisms of this higher geometric object are. And nicely enough, we have a counterpart of the clutching theorem for bundles, which means that if I have a germ, it defines for me this collection of local, this simplicial 2 form on N, and up to a cocycle in Beilinson-Deligne, and vice versa. So a natural notion of isomorphism is, well, 2 gerbs are isomorphic if the corresponding classes in Beilinson-Deligne cohomology are equal. And well, all right. Let me maybe stop here, and I'll take it from the next hour.
Okay, so now I pause recording and please remind me.
Slide. All right, so we have the right notion of gerb isomorphisms. So now these geometries, these are no longer just maybe the take-home message from this slide, which is terribly complicated, but it seems to be precise, is that isomorphisms between gerbs geometrize, so these equivalence classes of simplicial two forms, they geometrize as rank 1 vector bundles, or alternatively as principal CX bundles with connection. Full stop. If you want to know how, then I'm happy to explain, but I'd like to move forward. The point to be remembered is that isomorphisms between gerbs are themselves described by bundles. And then, again, you don't equate bundles. You look for morphisms between them. So there will be secondary morphisms between one isomorphisms between gerbs, the so-called two isomorphisms, and it just so happens that the whole bunch conspire to give gerbs the structure of a weak two category, the bicategory. But sort of never mind. So we have the notion of a gerb one isomorphism, which is modeled on a principal CX bundle. And now we can start discussing symmetries of our field, two-dimensional field theory, which is now defined in terms of the Cheeger-Simon differential character, and not in terms of tensors. What are they? Well, there are those guys which preserve. So I have a group. The group is acting on M, and there is a notion of pullback of a gerb, just like there is a notion of pullback of a bundle. I could explain how it works. Suffice it to say, there is a notion of a pullback of the gerb. That's it.
Of what?
Of a gerb. So the gerb was this higher geometric object. And so symmetries, if I think of symmetries as group, for the moment, just group actions stabilizing the action functional, here are just group actions which stabilize the Dirac-Feynman amplitude. So this Cheeger-Simon's differential character. And since I told you that fixing the holonomy, so fixing this character, fixes the isoclass of the gerb, this means that symmetries are now one isomorphism of the gerb. All right, so we have the first notion, which is an element-wise presentation of the symmetry group. So imagine that there is a, say, Lie group acting on M, and this should give, there should be a mapping from this Lie group to the set of isomorphisms of a given gerb. So for each element in the group, there should be one isomorphism. And you can measure the obstruction to the existence of such an element-wise realization in terms of the appropriate cohomology. But yeah?
Do you mean that this group acts on the space-time?
The group, no, the group acts on the configuration space, so on M, into which sigma is mapped.
I have M.
On M. And M is not space-time. No. Sigma is for me space-time in this talk. All right? Okay?
We started with them as a space-time.
All right, but then of course this is not all. We'd like somehow to make sense of homomorphicity of this element-wise representation. So for every element in the group I have one isomorphism. Is there any way to give meaning to homomorphicity? Can I make this realization homomorphic? For that, we need two more notions from higher geometry. So first of all, and well, there is a way to make it precise, but let me just give you a concept. If I have three gerbs and one isomorphisms between them, then I can associate with a pair of one isomorphism the so-called composite one isomorphism from the original gerb to the last one. That's it. How it is done? It's done in terms of Brzezinski's contracted product of bundles associated with gerbs. With the one isomorphisms. That's technicality. There is a notion of composition of one isomorphisms of gerbs. And another thing that we need, and which I heralded before already, there are morphisms between morphisms. Since one isomorphisms are modeled on bundles, then there are isomorphisms of those bundles, and these are the so-called two isomorphisms. Now, with these bricks, let's say, which I haven't explained in detail because it would have taken well, 2 weeks, for example, a course, a proper course, let me tell you what a homomorphic realization of a symmetry group acting on M lifted to the gerb would be. Well, I have a gerb, I can pull it back by the action of one group element, and then I can pull it back by the action of another group element. Then I have one isomorphisms, but I have G and the pullback of the gerb by the product of the 2 elements, so I can go there directly. And if I have a 2 isomorphism between these two, the composite 1 isomorphism here and the 1 step 1 isomorphism here, then I say that I have a homomorphic presentation of the group. And again, there is an abstraction in general of this object. And finally, I'd like this presentation to somehow reflect the associativity of the group action. Sorry, of the binary operation on the group. What do? Well, imagine I consider 3 group elements. I may pass from the gerb to its pullback by the triple product, either directly, as indicated here, well, it should be the opposite direction, or first by H3, then by H2, then by H5. And the 2, with the 2, there are sort of 2 ways of grouping these elements when passing from here to here. I may first group these 2 and apply my phi, and then group apply phi to the resulting 2, or I may group these ones, obtain by phi, fuse them and obtain something like lambda H2, 3, and then fuse these 2 ones. And the 2 ways of getting from the upper 1 isomorphism to the lower one should be equal. And in this way, I have an abstraction to an associative presentation of the symmetry group, which again defines a class. So the abstraction lives in H0 of M with values in U1, and this happens to be U1 to the power the number of connected components of M. So this is really a number, and these numbers will play a role later on. Okay, so what do we have? Conceptually, and I insist on conceptually, we have the following situation. We have a stratification of our space-time into domains which map into opens over which the 3 form trivializes. Then we have edges of this tessellation of the space-time sigma, which map into intersections of those opens, assumed contractible, on which there live 1 forms, which compare the 2 Bj and Bi, and then we have trivalent vertices of this tessellation. I can always choose a honeycomb tessellation of sigma, which map into triple intersections of the opens on which H trivializes, and from there I pull back the transition mappings of the gerb.
So this is sometimes called frequentization.
Well, for the reason that I named, because it transgresses to the loop space, precisely. Yeah. But you see, when you look at the formulae, nothing prevents you from generalizing this setting. Keep the decomposition, so tessellation of sigma. But now, map domains into manifolds. So stratify M. Map sigma alphas into M's. Map edges of the tessellation, separating the domains, into another manifold. And map trivalent vertices of the tessellation into yet another manifold. All that matters in order for the Chida-Simons character to be well defined is that these objects, so a gerb on M now, which was previously represented by BIs, a gerb one isomorphism on Q into which the edges of the tessellation are mapped, which was previously represented by the 1 forms, now it's a bundle with connection, and 2 isomorphism for the trivalent vertices, that they satisfy the simplicial identities. That's all you need to define the Chida-Simons character again, but for this much more general situation, which is what I drew at the very beginning of my talk. Now I have domains which map into possibly into a stratified target space. I have edges which map into their stratified target space, and I have vertices, for the moment trivalent, which map into their stratified target space. All I need is a simplicial structure on this object, which makes this guy a simplicial germ. Just like previously, I had a simplicial two-form, and that was what I needed to define the Chigi-Simons differential character. So I'm just restating the fact that I'm dealing with a simplicial germ over this stratified target space. And again, I can sort of formally, of course, I can go to details as deep as you want, but formally, conceptually, we have the same structure as all along. So just now, we have a simplicial germ over a simplicial manifold, into which a simplicial deconstruction of space-time is mapped. All right, so there are a few facts of life concerning these defects that I'd like to mention. So first of all, of course, in the domains, you have the same field equations coming from the Chigi-Simons differential character as before. So Lorentz type distorted minimal embedding. But what about defects? Well, as defects, you have defect boundary conditions, except these are not boundaries, but defect domain walls. There is a momentum, kinetic momentum transfer, which is controlled by this omega, which entered here. A two-form on the target space into which the edges of the tessellation get mapped. And actually, if you think of this equation, this kinetic momentum transfer at a defect, at a domain wall, as a relation for kinetic momenta and the configuration at the defect in the two-phase space of states, we have a defect, we have a phase to the left of it and a phase to the right of it. I can form a two-phase space of states equipped with the minus sign symplectic form coming from the left, from the right, and ask, what is this condition? It defines a subspace, a subset in this two-phase space of states, and it's isotropic. So it defines a symplectic relation, which is covered by the transgression of the the one isomorphism, which I pull back to the defect line. Well, I would comment, but let me skip it. That in fact, in this case, in this setting, we can give a meaning to Dirac-Feynman amplitudes for sigma with a boundary. It's just that what you have is a defect to the left of which there is your theory, and to the right of which there is nothing, an empty theory. And you may discuss what you didn't discuss in the first place. So we focus on the Aharonov-Bohm effect, so coterminal histories of a loop. Now you can do paths of loops. You know what to put at endpoints, namely trivializations of the germ. At the other extreme, we have defects which implement symmetries that I discussed. What you do is you have a defect at which the field jumps by a constant element in the group. So the group element multiplies, so to speak, the field configuration to the left of the defect and makes it into the field configuration to the right of the defect. Just action of a constant element in the group all along the defect. All right. So the problem with this formulation is that I had to stop at trivalent vertices, because that's how far my intuition, coming from the original discussion of the simplicial two-form for the germ, reached. But of course, I would like to have a generic picture. Let me quickly go to it. I'd like to have a generic picture in which I have an arbitrary number of defect lines converging at a defect junction. What prevents me from doing this? And so I'd like to somehow find an organizing principle for defining such models in a consistent way. And the organizing principle is simpliciality. So simpliciality. So what I would do, I would again have a decomposition of my sigma, of my spacetime, a simplicial decomposition of my sigma, and that would be mapped into a simplicial manifold, simplicial configuration manifold, simplicial configuration fiber, I should call it. On the first element of that family of manifolds, there would be a chirp. That's for the phases. It could be further stratified, no problem. For the edges, I would have another manifold on which there would be one isomorphism. For the trivalent vertices, it would be another manifold, and there would be those fusion to isomorphism. But the question is, what do I put on the other guys? What do I put on the other guys? And just to make this simplicial, or this organizing principle completely explicit, so I assume this to be a simplicial manifold. So these are the, well, semi-simplicial for the moment. I will not go to simplicial, although this is quite physical, so to say. But I have the phase map.
Do you get something like homotopy structure? Or?
No, I don't see a homotopy structure here. Well, so let me.
It is, I mean, cocycle up to homotopy.
No. That I will go there. So I will consider descending data and non-descending data. Of course, I won't consider them, but I would in principle, because that's also very interesting to have up to. And this is quite rich as far as information on the field theory goes. All right, but I'd like to have this standard picture in which I have an arbitrary valence, a defect junction of an arbitrary valence, and then, as shown by Runkel and myself, what I should pull back to such a defect junction is a very particular two isomorphism. So first of all, this defect junction should be mapped to a manifold, which comes with as many maps to Q, the manifold into which defect lines are mapped, as there are defect lines converging it. That's clear. I mean, if I map this point to Tn, I should go back to the limiting field configurations, as many of them as there are lines converging at the defect junction. So it should be Tn mapping directly to Q and not to Tn minus 1. I have a simplicial object, so there are many ways to go from Tn to Q. Just to, right? I have a Tn. And in the standard approach to defect theory, I would have Tn mapping to Q. Instead,
the dimension of n you fix as 2 or not?
Come again.
Dimension of n you fix.
None. No fixed.
Yeah, so then you have check cocycle of arbitrary rank, yeah, so
No.
degree.
No. Well, here the degree will be fixed by the dimensionality of sigma instead. And I'm starting with H, which is a free form. So the free form will have, there will be a 3 form and 2 form and 1 form, and that's it. No more to it. There won't. Okay, and now the point is, so how do I get from this simplicial picture to the picture in which I have Tn mapping directly to Q and very specific two isomorphisms using these maps? Well, simpliciality is the answer. So using simpliciality, the combinatorics of the simplicial manifolds, I can induce uniquely and as many as need be, and not a single more, maps from Tn to Q. These are just concatenations of the phase maps of the simplicial manifold. And having phi 3 on T3, I can pull back phi 3 to Tn in many ways. And that's the whole point. So it's good to develop a graphical presentation of this simplicial induction mechanism in order to understand how I arrive at these results. So you see, if I have a junction with 1, 2 to n plus 1 lines, it's good to think of this pinching mechanism where I choose two adjacent lines and introduce a virtual edge between these two lines and the rest of the defect graph for an n plus 1 valent junction. Each such pinching is represented by a phase map in an obvious manner, right? So it gives me this point, and finally, after so many concatenated phase maps, it gives me this point. So this is a mapping from Tn plus 1 into ultimately into, well, Q, which is where the defect line goes, or T3, or T3, if I stop one step ahead of actually selecting a defect line. So, what about the induction of two isomorphisms for junctions of arbitrary valence? Well, for these, I need what I call ternary resolutions of binary trees representing defect junctions of arbitrary valence. So, by concatenating phase maps of the simplicial manifold that I started with, I can associate with any such ternary resolution of a defect junction of valence here 9 plus 1 10, a collection of maps to T3. And using each of these maps, I can pull back phi3 from T3, and in this way induce a two isomorphism for the higher valence defect junction from the ternary ones. Well, these are the maps. I worked them out for you for this particular ternary resolution of the 10-valent junction, and I can simply, in an algorithmic way, induce a two isomorphism for this higher valence defect junction from phi 3s. Well, another point you see is that for any two resolutions, I have a finite sequence of associator moves taking me from one resolution to another. So in order to have a unique assignment of a two isomorphism to a higher valence defect junction, I only need to impose the condition that the associator moves induces the two isomorphism for the 4-valent junction in a unique manner. But that happens to be the condition of simpliciality on the Ger G phi 3. So you see the framework sort of closes on itself. So if I really have, just to go back here, if I really have a simplicial Ger on this simplicial manifold, then I have a unique way to define defect junctions of arbitrary valence. Data for defect junctions of arbitrary valence. All right. So you might say that this is just abstract nonsense, so to speak. So is it useful in any way? Let me go back to the motivating example that I started with, namely gauging of a symmetry. We already know how to describe categorified symmetries. So those families of one isomorphisms of the germ, or element-wise representation of the symmetry group acting on M, then two isomorphisms labeled by two elements in the group, and then these should satisfy some associativity condition if I want an associative realization of the group. I may now ask the question, can I gauge this rigid symmetry as represented or categorified by these data? So not just a jerk, but a jerk one isomorphism, collection of jerk one isomorphisms labeled by elements of the group, and a collection of two isomorphisms labeled by pairs of elements of the group. And the answer is yes, and it's a simplicial structure, and it's a simplicial jerk. This is actually a motivating example of a simplicial jerk, which I will precisely pull back to this picture that I started my presentation with. So just to go back, the picture that we had was, we have our sigma, which is two-dimensional. We split it into domains over which the principal G bundle, G being the symmetry group that we're gauging, trivializes. There we have local sections of the principal bundle. By the local sections, we pull back the Eresman connection. So we have local gauge fields on the domains. Now the domains are two-dimensional, so they are separated by one-dimensional domain walls, and these domain walls intersect at points. And now I'd like to, in the presence of the jerk, which I pull back to the domains, I'd like to make sense of this topological / differential geometric construction, Cartan-Borel namely, with Eresman connection that I presented at the beginning. But now we have the jerk. And what do we do with the categorified symmetries? How do we gauge categorified symmetries? And the answer is, do as I discussed just a moment ago, but choose a very particular simplicial manifold. I'm mapping, and actually this picture is telling you which manifold to choose. I'm mapping the domains of trivialization of PG into my manifold M, on which the group G acts. At defect junctions, I have field discontinuities. The fields are taking values in M. The defect domain walls, the field jumped by an element in the group, namely the transition mappings of PG. So they should be mapped into G times M as follows. At defect junctions of valence M, I have just so many different transition mappings with so many different indices. For example, for G2, I have the reference value of G, one jump, second jump, the third jump is already fixed by the previous two. So I have a mapping to G to the power 2 times M. And this altogether will form the nerve of the action groupoid of G on M. And it is over the nerve of the action groupoid that I will construct a simplicial germ in order to gauge the categorified geometry. For that, I need to do two more things. I need to identify the tangential rigid symmetries. I will then stumble upon a certain Grau algebroid and the Dirac structure in it. And then I have to perform some minimal correction of the original Chigga-Simons character for PG trivial, which is what is happening over sigma alpha. Okay, so first the tangential symmetry. When using the Chigga-Simons, using the defining property of the Chigga-Simons differential character, I find out that for a group action to preserve the action functional, the corresponding fundamental vector field, whose definition I recall here, should have the following property. If I contract it with the 3 form, the curvature of the Chigga-Simons differential character, then it should be exact. That's a cohomological property, I can explain it, but let me just say that this is so. We tend to refer to this kind of relation as quasi-Hamiltonianness of the fundamental vector field. Because, well, if you have omega here, that would be the definition of a Hamiltonian vector field. And then, so you see that tangential symmetries are actually pairs, a fundamental vector field and a global one form. Well, these are sections of Hitchin's generalized tangent bundle, tangent Whitney sum with cotangent, and on these there happens to be a very particular algebraic structure, namely that of a Courant algebroid with the following bracket of sections, which I now correct a la Chevera and Weinstein by the 3 form. And then, lo and behold, this bracket closes on symmetric sections. So if I have a quasi-Hamiltonian section like that, and I take 2 such quasi-Hamiltonian sections, then their bracket is a quasi-Hamiltonian section. So that already is beginning to tell you that maybe you should keep track of this extra structure on infinitesimal symmetries. And indeed, so now that was just a stray observation. We'll make sense of it in a moment. Now I have to understand how I should correct the original Chigga-Simons differential character using the local gauge fields A alpha coming from a principal Ehresmann connection on PG, and PG is locally trivial over sigma alpha, how I should correct the original Chigga-Simons differential character in order for the corrected character to be first invariant under small gauge transformations and then large gauge transformations. Small gauge transformations are those from the connected component of the identity gauge transformation, and the large ones are from the rest. So then how do you correct this Chigga-Simons differential character? That goes under the name of minimal coupling. So you introduce in the action functional a polynomial of the gauge fields with functional coefficients, the functional coefficients being depending functionally on the point in M. That's the standard procedure. And it turns out that in order for the corrected, polynomially in the gauge field, corrected Chigga-Simons differential character to be invariant under small gauge transformations, this correction, polynomial correction, has to take the following form. So it's a two form whose exponential you're attaching to the Chigga-Simons differential character. It is fixed by those co-momenta, so those one forms, and their contractions with the fundamental vector fields. Well, here's a formula for you, all right? But now the point is that this is so the corrected action functional is invariant under small gauge transformation if and only if the functional span of the symmetric sections of this Hitchins generalized tangent bundle actually has a vanishing Jacobi and Leibniz anomaly, so becomes a Lie algebroid. And then once it becomes a Lie algebroid, it can only be one and is the one, namely the tangent Lie algebroid of the action groupoid that we saw previously. So that's the thing that we obtain. So the obstruction against gauging has two levels, the tangential level and the global level. The tangential level is this one, and the obstruction is that of having a Dirac structure within the Shevara-Weinstein corrected Courant algebroid on the Hitchins bundle, on the Hitchins generalized tangent bundle. And then, well, secretly what it tells you, I phrased it in a way that I fancy, but secretly what it tells you is that those KAs define for you an equivariant extension of H. We're doing equivariant cohomology just in disguise, in Courant algebroid disguise. And you won't be surprised since these conditions actually tell me that I have a class in equivariant cohomology, which is the homotopy model for the RAM cohomology of the orbispace. So I'm back to Cartan-Borel mixing diagram. It has to geometrize. So for large gauge transformations, I have a geometrization of this equivariant cohomology class given by what is known as an equivariant structure of the germ. And that, to go back to the simplicial object, is none other than a simplicial germ over the nerve of the action groupoid. And that's what I need to gauge this categorified symmetry. The global structure behind it that is responsible for, because I chose to use the local sections of the principal bundle PG to discuss those discontinuous field configurations, and then I played with the local gauge potentials and so on and so forth. But remember that at the beginning I actually had something beautifully smooth and global, like global sections of the associated bundle. So let's go back there and appreciate the relevance of the equivariant structure from that point of view. Sort of let's shrug off the technicalities. And so here the result that sort of governs the whole business is this equivalence of two categories. So if you want to know what the bundle gerbs with connection on an orbispace of a group action, assume smooth, are, so this bicategory, as it happens, is equivalent to the bicategory of bundle gerbs with connection on the covering space of this orbispace, but with extra structure. And this extra structure is an equivariant structure. But wait, you might object, but if I have a gerb over M, then M mod G needn't be smooth. But this is not where I apply this theorem. What I apply this theorem to is I follow my Cartan's recipe. I replace sigma times M with PG times M. I put the gerb here on M. I have the Ehresmann principal Ehresmann connection on PG. And then I have this correction, which I saw in the local picture of the pullback gerb from M. And this is supposed to descend from PG cross M to the quotient manifold, which is the associated bundle. And indeed, this is what is happening if I had an equivariant structure on G. And since I phrased all these constructions in sort of cohomological terms, there is a way to identify the obstruction class for the gauging, and there is also a way to classify inequivalent gaugings. This is going to play a tremendously important role when we sort of discuss T-duality in terms of gauging, but that will have to wait. So now, quickly, of necessity, what if, as Janusz asked, what if the thing doesn't descend? So I don't have a simplicial object. It's simplicial almost, up to a point, it's simplicial. And it turns out that it tells us a great deal about the two-dimensional field theory. This is remarkable. The simpliciality is really a strong feature. So in order to appreciate it, I will stick with symmetries. I like them. So what better manifold to discuss symmetries than the group itself? So I will map sigma into the group manifold, and I will discuss symmetries that have to be in the game. So the group acts on itself, say from the right, by right translations. Whatever field theory I define on the group manifold, it had better have this as a symmetry. So what I'm building secretly is the action groupoid of the right action of the group on itself. So I already see that Q should sit in G times G, implementing jumps by elements in G. And the target manifold for the domains, for the phases, is G. Okay, but you see, G is also a G squared manifold. So G times G acts on G from the left and from the right. So I now enhance the principle of simpliciality by G squared symmetric simpliciality. So basically, I want to think of the nerve of this action groupoid as a G squared manifold. I have the left-right action of G on itself. I propagate it along this simplicial manifold by requesting that the face maps of the simplicial manifold be equivariant. And in this way, I fix the action on higher members of this simplicial manifold. And then I introduce another rule, and this is all sort of motivated or sort of justified ex post. It gives very interesting results, insights into this field theory. I introduced, to have triple S principle, I introduced the principle of semi-simplicity. So on internalizing the nerve in the category of G squared manifolds, I decompose its components into orbits. So I have full reducibility. I reduce it. And then what I have, well, how could I define this two-dimensional field theory in such a setting? Well, luckily I have a canonical choice of the metric for the metric term, that's Cartan killing metric, and I have a canonical choice for the threefold, namely the Cartan threefold. And you might wonder why I have put the same normalization in some strange pies here. The reason why I did it, is, well, first of all, these two forms are G squared invariant. That's a good thing. And then the co-normalization means that I don't just have G squared symmetry, but a loop version of it in this field theory defined as previously. And moreover, why did I choose H of this form? Because for G good, which means compact, connected, and simply connected, this is the generator of H3. And well, then you have to fix the data for the defects, and you see, by demanding that the kinetic momentum transfer condition, which occurs at the domain wall, and at the domain wall we have a jump by the action of the group on itself on the right, that it be preserved not just by constant jumps, but by the loop jumps, we actually fix the curvature of this one isomorphism that I pull back to the defect line. And since I don't want to prolong my talk, and I'm slowly coming close to my time is running up, let me just show this as an example of how the three rules, principles, simpliciality, symmetricity, and semi-simplicity actually fix something for us. They actually fix the data of the defect. And I don't have time for that, which I regret terribly, but they would also go a long way and in fixing what I should put on defect junctions for this particular defect, implementing the right translations on the group. And there are beautiful relations between the thus obtained higher geometric structures and a certain topological field theory, which was shown by Gawęcki to be symplectomorphic to the so-called topological sector in this two-dimensional field theory, namely Chern-Simons theory with Wilson lines, which is known otherwise from its deep connections with the theory of moduli spaces of principal bundles on punctured Riemann surfaces. And this is precisely what I'm seeing here. And I do regret that I don't have time to really tell you about it, but I think that's for the better. So let me just sum up by telling you where it goes from here. So where it goes from here. So first of all, by applying this framework finds fantastic applications in the construction and classification of both phases or domains and boundary defects, also for non-one connected E groups. That's via orbifolding that was done by Gawęcki and Reis. Then we have tools for the construction and classification of phases of this model over non-orientable spacetimes. That's something that people from string theory corner of the world get excited about. Then we have more general dualities, such as T-duality or mirror symmetry, if you will, sort of accessible via this higher geometry. These constructions can be transcribed as done by Di Fiorenza, Sati, Schreiber, and Staszek, and also independently and better by myself. They can be transcribed into the Z2 graded category, so with supergeometry with supersymmetry. And there is also something about emergent spectral non-commutative geometry twisted by the Germ, where the spectral geometry is the Fröhlich-Gawęcki spectral geometry of loop mechanics, the sigma model. And now the future directions, which are pursued currently, so extending the gauge principle beyond group actions, that's for groupoidal symmetries. So in other words, descending the field theory from a manifold, which is foliated, to the space of these, where we have general groupoids. That's what we're working on with Thomas Strobel. Then looking for T-duality defects and explain them via T-duality via gauging of toroidal actions. That's what we're doing with, or beginning to do with Kalin Lazaroiu. And then I've spoken about abelian gerbs. There's a beautiful way of weakly de-abelianizing gerbs, or we believe there is one, because there is one bundles that was worked out by Lazaroiu and his collaborator Shahbazi. And so this is something also that we'd like to understand. So thank you very much. And I'm sorry I couldn't give you all, I couldn't bring it to the end. Thank you very much. Thanks. Tak jest,
And I'm very sorry to tell you that we really don't have time for questions now, because on the other side of the door, there is probably a group of people waiting for their seminar. So the only thing we can do is to stop recording and wait for the next week when there will be Daniel Beltita speaking.
Yeah, thank you very much.